All righty. Well, thank you all for joining us at this Year of Climate and Carbon webinar. Today, we are welcomed by and joined by Peter Lawrence and Monica Morrison from NCAR's Climate and Global Dynamics Laboratory. And today, um, they are going to be talking to us about climate global modeling and how some of the measurements that we may be collecting within the GLOBE program may also um, be able to become part of these larger climate models. So I'm really excited for everyone to be joining us today. Feel free to add questions in the chat as Monica and Peter are presenting, but I'm going to go ahead and pass it off to you two. Thank you again for being here.
Hey, great. Thank you. Yeah, so as Grace said, I'm Monica Einhorn Morrison, and I'm joined by my colleague Peter Lawrence, and we are both in the terrestrial sciences section in the Climate and Global Dynamics Laboratory. And today, Peter is actually going to be giving a presentation on the nature of Earth system models and pointing out the ways in which Earth system models treat things like the carbon cycle and integrate in or use measurements like the ones that you might be taking, both to inform the development of what we call parameterizations or treatment of small scale processes in our global climate models, or use them for validating on models so that we can make sure that they're actually consistent with reality and what's happening in terms of how processes are actually behaving in the real world. And so Pete's going to give a presentation for around about 40 minutes. And then I think we're going to open it up for questions. And along the way, if you do have questions, you can put those in the chat, as Grace had said, and I can either answer those on the fly by responding to your chat message, or if it's a clarifying question, something that Pete has said, I might just go ahead and a little bit of a warning, Pete, interrupt you so that we can get an answer to the question before moving on. So Peter, I think, do you have the ability to share your screen? Because I don't want to take up too much time from you.
Thanks, Monica. Yes, no problem at all. As Monica said, I'm going to give this presentation in two parts. The first part's going to be a higher level sort of system modeling that we do in at the National Center for Atmospheric Research in the Climate and Global Dynamics Laboratory. And the second part's going to be specifically looking in at some of the work that we've got as part of an NSF grant looking at climate interventions. And these are looking at ways of trying to go through reforestation, afforestation, or some forms of bioenergy with carbon capture and storage, looking at those and seeing how we can model those types of ideas inside our Earth system model. So without any further ado, I'm going to share my screen and we can start. Okay, so this is a talk, it's an overview talk, and I'm going to acknowledge the CSM Chief Scientist, David Lawrence, who's my boss, no relationship. We just share the same last name. And this is a talk that we've been putting together around about all the Earth system modeling we do with the Community Earth System Model. This is a model that is basically supported and managed by NCAR and principally through the Climate and Global Dynamics Laboratory, but we also work closely with all the other laboratories here at NCAR and with our wider community, which is both university and researchers across the world. Sorry. Just to start with, basically, what is the CSM? It's this continually evolving Earth system model. It's one of the premier Earth system models in the world. It's used by thousands and thousands of researchers to look at Earth system modeling. We really focus on the community part of that. That's why it's the first word in Community Earth System Model, is because this is not just an NCAR model. It's not just a UCAR model. It's not just a National Science Foundation model. It's actually a model built up by a community of researchers. And what is that model? Well, basically, it's a model that's been developed to try and understand the Earth system, both in terms of its, the way it's evolving and the climate emergency that we're currently facing. So we can look at doing adaptation, mitigation, and intervention needs. Sorry. So when we talk about Earth system models, what are we really talking about? Well, we're talking about process-based models. And what does that mean? Well, it means that rather than being statistical models, these models actually simulate the whole world as it is, represented through mathematical formulations of both state and fluxes and changes. Sorry. And so each of these processes, each of these components of this model are trying to represent the world at a 30-minute or an hour or a daily time step. So if we were to look at, say, like the land component of that, we have all these different ways of representing it. So we can say, where is the vegetation? Where are the crops? What are the dynamics of those crops? What does the carbon cycle look like there? How do plants grow? How are they affected by climate? The same thing happens with our river system. So we could say, well, the water that's running off the land, where does it go? How do we know where it's stored? Where does it flow into the oceans? We can also look at the atmosphere, and we have three different ways of looking at the atmosphere. Sorry, we've got some noise there. Can we?
Yes, if you have your mic on, please turn it off.
So the atmosphere can be run either in like a more efficient, what we call CAM7, which is a community atmospheric model, which allows us to do the troposphere and the mid level of the stratosphere, or we can go all the way through to the top through the mesosphere and the thermosphere out into space. We can also look at chemistry in the model. We can look at sea ice. So where is sea ice forming? How does it change? What is its dynamics? We also look at land ice. So how do glaciers work? How does Greenland work? How does Antarctica work? And finally, we're looking at the oceans. So what happens in terms of overturning currents? What happens in terms of sea surface temperatures? How do the oceans interact with the atmosphere? And all of this is held together by a coupler. And so that's a flux coupler. So it says, if something evaporates from the ocean, it'll move through the coupler into the atmosphere. So it'll go through the surface layer, into the boundary layer, into the atmosphere. Same thing happens between the land and the rivers, or the land and the atmosphere. So you can see this whole thing is an integrated coupled model. And it's like millions of lines of code continually running in time to try and work out how all these elements work together from both an energy, a carbon, a radiation, a water perspective. Okay. So one of the key things we're doing is we're taking this model and it's continually evolving. So you might have heard of what's called the coupled model intercomparison project. This is where all the major Earth system modeling groups around the world run both historical and future projections of climate and try and see how their models respond to different scenarios and different historical reconstructions. So this allows us to say, well, okay, these relatively independent versions of the model, what do they tell us about the world? And so when we bring them all together, we get what's called the multi-model ensemble, or the shared understanding of how the climate system works. So what we're doing right now is we're developing a new version of the model, which is CSM3. CSM3 is set up so that it will be able to be used in the next community model, the coupled model intercomparison 7, which will go into formulate IPCC's working group 1 for the next IPCC assessment report. It also fits into the global stocktake. So what we're trying to do is work out how do we set it up so that we can have a model working and ready for the next levels of these global assessments. So what happened is in CMIP 6, we had reasonably uncoupled Earth system model. What happened is like we had the atmosphere and the oceans and the land all working together, and they had interactive aerosols, but the carbon cycle was typically like prescribed. So we'd say, well, in this particular year, the CO2 concentration is this. For CMIP 7, we're actually including the carbon cycle. So we're going from being, and there were carbon cycle runs in CMIP 6, but they were only a very small number of them. Now we're looking to transition to having the carbon cycle is foremost in this part. So that means that when a forest is cut down and it burns or it transforms, that carbon is put into the atmosphere. The atmosphere then works out where it goes, whether it goes, some of it goes in the ocean, some of it stays resident in the atmosphere, and that affects climate. So our models are becoming more representative of the processes that we're really interested in exploring. sort of key areas of what we've done with the recent version of the model. We have run large ensembles, which means that we can look at the model internal variability of a model. So what happens is, depending on the initial conditions, and even a small difference in initial conditions for an Earth system model at the beginning of a time period can lead to a difference in terms of the outcome of that climate. So this is like the chaos theory. This is like the butterfly effect. What happens is basically you get a slightly different climate if you start from slightly different a starting point. And that allows us to understand the internal variability of the system. So the large ensembles, 100-member ensembles, where they all started with slightly different initial conditions, but all 1850 climate. And they ran out through the historical period. And then they used SSP 370, which is a high warming scenario, to run from 2015 to 2100. What we were able to do then, so you get some idea of like what the model looks like, internal variability versus the mean. And so this is what we've got over here on the right-hand side, this plot here. And so the black one shows what the large ensemble looks like as it goes through time. You can sort of see from 1920, you're sort of like the reasonably flat. There's a cooling period with like the large amount of aerosols that were associated with like coal-fired power stations in the 1960s and 70s. Then we see this warming occurring through to where we are right now in about 2020. So this is 370, which is a warming situation where so we end up with like the temperature normally ends up over 2 degrees of warming. So it exceeds both the Paris agreements for 2100. Actually, this is only going to 2050, sorry. So we're exceeding the Paris agreement before 2050. We can also do things, because this is a model, we can do things like we can put all the things that are forcing the system. So whether they're land cover change or aerosols or fossil fuel emissions, we can put them all into the model, and that's that black line. Or we can just look at what happens if you just put the greenhouse gases in, which is the red line. So you can see that the red line, just for greenhouse gases, is a lot stronger warming than you would get with all of the forcings. You can see the blue line down here is just the aerosol forcing. So what is the effect of like having black carbon and sulfates and things in the atmosphere? Well, it's actually quite a strong cooling. So when that strong cooling meets that strong warming of the greenhouse gases, we end up with like this this other sort of combined effect, which is the black line. Okay. The other graph here shows what happens in terms of snowpack. And so we have pretty strong relationships between runoff and snowpack in the historical period. This is in high mountain areas. But what happens is that if we look at SSP 370, that relationship starts to break down. So we end up having, you know, the relationship between the snowpack at the end of winter and how much runoff you get suddenly is like all over the place, depending on which year you're in. And this is because we've got a lot more energy in the system. There's a lot more evaporation. There's also a lot more of the soils are drier because it's hotter and warmer world. Okay. What I want to do is like move into maybe some of the newer developments and some of the capabilities. So typically we run our model at about 1 degree resolution, which is around about 100 kilometers per grid cell. So you can imagine the whole world divided up into 100 kilometer grid cells. But we've also done a lot of high resolution simulations where it's like either 10 kilometers or 25 kilometer resolution. So 0.1 degree or 0.25 degrees. And what happens is as we like make the model finer resolution, we get more detail, we get more components of the model being represented. So, sorry. So we're also doing decadal predictions with these high resolution models. So we can start saying, well, what happens over the shorter periods of time coming forward? So one of the key things you can think of is like extremes, because extremes are one of the things that low resolution models don't do very well. They sort of smooth everything out. But so what we can see here on the right-hand side is the 99th percentile of daily winter precipitation. So this is sort of like saying, where is the most intense precip happening? And in the low resolution version of the model on the right, you can see it's kind of smoothed out. You don't pick up the orography, all the mountains on the west coast, and you don't get these sort of these systems working as strongly and intensely across the southeast. Whereas when you go to higher resolutions, you start reproducing some of these more intense and these more extreme sort of climate phenomena, these weather anomalies. We're also starting to look at climate interventions. So what are climate interventions? If you think about climate interventions, we're talking about going beyond just mitigation. So mitigation is the most important thing. You're not going to be able to address the climate crisis without doing mitigation. Unfortunately, we're at a point in time now that mitigation alone is not going to allow us to have a climate that's going to avoid exceeding 1.5 or 2 degrees Celsius. Even the strongest mitigation right now, given the political sort of commitments, what we've seen at COP in terms of like the nationally declared contributions or commitments, these NDCs don't get us to the Paris targets. So one element that is being talked about is large-scale carbon dioxide removal. So this is like if you were looking at reforestation, afforestation, or looking at bioenergy with carbon capture and storage, so that you grow a bioenergy using crops, such as switchgrass or miscanthus. You then capture the carbon dioxide that is released when you are generating energy. There's also things like soil management, or there's a lot of work in terms of oceans. Can we like farm kelp and then be able to use that kelp for either for biofuel products or as a storage of carbon? The final element that's being discussed is looking at solar geoengineering, such as stratospheric aerosols. Like, so we would try and reproduce what happens after a major volcanic eruption by putting sulfates particles back into the stratosphere. So we noticed that after the Pinatubo and other major volcanoes, we see the strong cooling as the stratosphere becomes more reflective to incoming sunlight. So the question is, can we like reproduce that? And in our models, we can. So the question is, well, what would the role be of that? And how practical is that? Are there unintended consequences, such as changes in rainfall patterns? So these are the sort of things we can do with our models. Here I'm just looking at the stratospheric aerosol injection I was talking about before. And you can see with no interventions on the left-hand side, this is a 2.45 world. So that's 4.5 watts per meter squared at 2100 imbalance. So this is like a lower warming scenario. It's not a Paris targets scenario, but it's lower than the other scenarios that are in the CMIP 7 experimental design. And what it shows is that by putting these sulfates into the stratosphere to try and mimic or replicate these volcanoes, we can actually offset some of that cooling in our models. The other one on the right-hand side here is looking at what's called marine cloud brightening, where stratocumulus clouds, which are low clouds over the oceans, are seeded with either salt or other forms of cloud condensation leak layer, and they make the clouds brighter and more reflective. So our models respond like that. One of the big problems with marine cloud brightening, as you can see, is that like causes these very large geographic anomalies. So we can see that in some parts of the world we get strong cooling, in other parts of the world we get strong warming. So the reason why we're doing these modeling experiments and exploring these things is to try and sort of work out what are some of the potential consequences of interventions that are being discussed globally right now. Obviously, what we see here with the very strong warming over the US and then over like the North and South Pacific and Antarctica would be terrible under a cooling such as an attempted cooling like such as this. Finally, under the bottom left-hand corner here, we see reforestation, afforestation versus bioenergy with carbon capture and storage as two different ways to try and remove carbon from the atmosphere. One of the things that you can see here is this very wide spread of uncertainties. And so like the uncertainties in terms of afforestation and reforestation are dependent on the carbon cycle, such as like fires, changes in mortality, how will the forests actually recover and do they benefit from elevated CO2 and changing in climate? But the bioenergy is really like the big question is, what are the efficiencies of fuel conversions of bioenergy? How much can you really capture? Can you really store it? So what we can see is like these uncertainties allow us to explore a world where bioenergy would be a big capture of carbon, but if we're at the other end of it, it could actually cause more carbon to end up in the atmosphere as if we'd done nothing. So we're really trying to explore these uncertainties before, you know, major policy decisions are put in place. One of the other nice things about sort of moving on now with our model, this is CSM can be used to do sub-seasonal to decadal timescales for looking at predictability. of this sort of longer range climate. So typically when we do a weather forecast, we have a high degree of skill going out maybe like 5-7 days. But once you get out beyond about 10 days, the skill of a weather forecast breaks down due to the fact that like there's a lot of chaos in the system, a lot of feedbacks and internal variability. But on longer time scales, there are actually elements of the climate system that give us knowledge, such as the oceans. And so we know that like if there are certain ocean configurations, that there's a high chance that you'll have responding longer term seasonal to decadal type responses. So our model does very well in terms of being able to give us information about that and help provide to other centers that are looking at trying to use that information. We also know that like the interaction between wildfires is really important. So this was a study that was done looking at the Australian wildfires of 2019, 2020, and its impact on ENSO, so the La Nina, El Nino forecasts. And what happened was that we found with this prediction system that if you didn't include those wildfires, what happened is you were coming along, and this is the SMILE black line. And the black line sort of like as it ran out into 2021, changed from a La Nina out to a mild El Nino. But if we put in the wildfires and the large amount of black carbon that ended up being evicted out of Australia across the Pacific and over the Central Pacific and into the East Pacific, there was actually a strong cooling that happened associated with that. And that actually put us into the red line here. So our system said that by adding these wildfires and all this black carbon, we're able to better project the La Nina of 2021. And here you can see is the blue dot is the HAD SSTs, which is the sea surface temperatures that were actually measured. And they meet up almost exactly with this seasonal prediction of El Nino, La Nina, with what's called SMILE, which is the seasonal to multi-year large ensemble. And so what we can say is that there are certain elements in the climate system that give us more understanding of what the future might look like. And by having a modeling system like this, really gives us the ability to try and explore those relationships. I'm going to move on to one next component of our model is like, so I was talking about having the resolution, the high resolution versus the low resolution. We also have what's called variable resolution grids. So here you can see a number of high resolution grids that sit. And so most of the world is at this coarser 1 degree resolution, but you might have a targeted study region that you're really interested in. And so we can actually have it so that our grid refines as you come into your study region, so that the atmospheric processes and the land processes and the ocean processes in those areas are at the much higher resolution. So they capture things like squall lines, convective systems, they pick up mountain systems, and you can get a lot of those advantages I was showing for the high resolution, but targeted over your region. And the reason why we want to do that is because it's very expensive computationally to run the whole globe at high resolution. And it might not be really that important for the questions you're asking. So by doing this, you can find a computationally achievable configuration of the model to answer the question you need with the resolution you need. And this is just an example of how we can do chemical traces in the model. This is fires that are happening on the West Coast and into Canada. And you can see how they're being emitted up into the atmosphere, and then they're transported up into the higher latitude jet stream, and they're like transported across the high latitudes. So this is a chemical tracing model, but it also captures aerosols and other things. And you can see this is on the right hand side is a DC-8 flight that was taken. This is a NASA NOAA DC-8 flight, just being able to capture what's happening in terms of emissions and chemicals going through the model. Okay. So there's a lot of other elements going on. I'm not going to get into this in a lot of detail, but like lots of people are using this Earth system modeling configuration to try and go very high resolution. So globally 3.75 kilometer resolution. So this is like what's called convective resolving or convective representative modeling. And so there's a lot of work going into that. Efforts at Colorado State University, efforts at NCAR, And we're seeing that a lot of energy and effort's going to that. But one of the big problems is it takes a lot of computer resources to do this, and that means you can't actually run the model for long periods of time. And you have a lot of troubles in terms of initializing the model and then analyzing that much data. So we're trying to run a hierarchy of models from these really high resolutions up to coarse resolution models, depending on the questions you're asking. I mean, there are a lot of features that come out of these high resolution models, such as squall lines, that we can see how well they represent. So the benefits of doing high resolution modeling. And there's a 40-day summer and winter plan for this year, this really high resolution modeling. But again, this is only a small amount of the modeling we're doing because it's so computationally expensive. One of the nice things about our Earth system model is we can do a lot of impact analysis. So this is the work that Monica and I are working closely on, is looking at the land model and what can we understand in terms of how both natural and human managed landscapes and systems are impacted by climate change and how they contribute to things such as the carbon cycle. Here we can see that we have like agricultural products being modeled inside. So we have a crop model. There's an urban climate, so we can look at urban heat islands. We can look at heat stress for humans in those systems. We can look at the water demands for agriculture. We can look at fire and logging of forests. We also have other systems, such as we have a marine ecosystem model that's built into the ocean model. Allows us to go from phytoplankton to zooplankton. And then we can use further models, such as the feisty fish model, to work out how fish populations are responding under changing climate. There is one of the key efforts that we're doing is looking at how we can take in artificial intelligence or machine learning methodologies. So previously, like we built up our systems from the bottom up based on theory and parameters that are measured in the real world. But now we're saying that, well, you can only sample so much of the world. And maybe machine learning has a place in terms of helping us constrain those metrics that we know from the real world and how our model behaves. So that's one element. And so we can see that like changing different parameters in terms of different elements of the system, the machine learning framework can give us insight and guidance to which parameters are uncertain, which parameters have large influences on emergent properties of the system, and what's a better configuration of the model that might give us a better understanding of the world. There's also machine learning in terms of doing downscaling. So downscaling is where we take our coarse resolution models, use Earth system observations, such as like reconstructions of temperature and precip, and pressure fields, and say, how can we take the modeled world and make it more useful and more applicable and more actionable for people? So that's also another area where machine learning is coming in. So that's basically, if you think about it, like a whole resolution of everything going from tornadoes through to the solar cycles. So we're looking at time scales and spatial scales, trying to understand how the model works in those scales. One of the nice things is, as I was saying, you can like configure the model for your questions you're asking. So if you have questions that are really sort of high level, you can use the standard 1 degree version of the model. That's what we're going to do for CMIP7. That'll be the new configuration, how we run the model. But if you want to do these high resolution, or you're really interested in certain parts of chemistry, or you're really interested in looking at how glaciers work, you can configure the models and answer those sorts of questions. Okay. One of the more recent things, and Monica's been very strong proponent and also organizer of this, is looking at climate justice. Like, so it's one thing for us to be doing experiments and running the models and being involved in these international efforts. But what does it really mean in terms of providing information to people who are the most vulnerable in the world, the people who have the least access to these modeling efforts? Are the models fit for those purposes? Do the models give you insight into the questions that need to be asked? And so she's been really, and she can talk about this later, but I just wanted to put that there. This is a really important component of what we're looking at. The other side, and this is another thing that Monica's been really strongly involved with, is trying to put in documentation so people can understand what our models are, what they're good for, and what they're not good for. So having this information is really important, so you don't misuse the models, or you know how to configure the model to answer the questions you want to be sort of exploring. And that sort of brings me back to the final part, which is looking at how does the community system model work? Well, it works with a community, and this is like our um, annual meeting that we have every year. We have it at Center Green now. We used to have it at Breckenridge, but we typically have about 400 people come to Boulder. We all interact. We have lots of sessions where we have talks and posters and planning sessions, and all of the ways that the model develops are discussed in these formats, but it's always a community focused. And that community focus is broken into these working groups. So, and these working groups are open to anyone who wants to join them. They're not a closed community at all. This is like it's open, and once you once you become a member of these working groups, you can contribute to the priorities, how the model's going forward, how the code gets used, what processes are involved. So there are currently 12 working groups, and you can sort of see like all the different things that you may or may not be involved with or interested in. You might not really be interested in software engineering, but you might really care about biogeochemistry, or you might really care about like climate variability and change. So these groups really have focused sort of themes to them. I want to just throw it out there as well. I'm on the CSM tutorial committee, so I ran the tutorial last year. And what we do is every summer, and that's North American summer, we have a week-long tutorial here in person. We have typically about 80 participants, and they get a series of lectures, hands-on practicals, and they get to learn how to run the model and how to use the model. This is really a successful way that we build our community and get engagement and bring the new researchers and the new members to the community into the community and give them the ability to be able to contribute and use the model for their research. Okay, this is my last slide for this particular part of the talk. And I just want to say that I'm talking about the community system model, but what's really true about NCAR, the National Center for Atmospheric Research, is we have a whole ecosystem of models. It's not just we have CSM. We have these different models such as MPAS. We have WRF, which is the weather research and forecast model. We have the hydro version of that. We have dynamic versions of ecosystems such as the FATES model. So we're not just one model, we're actually more an ecosystem of models. And on that, I'm going to end this part of the talk, and I'm going to close that.
So
Now,
Pete, really
yeah.
quick before you go on, I wonder if you can comment on two things that came up. So one is whether or not various sorts of ground observations, how they relate to the model development, the model validation. And I talked a bit about the instance of clouds, and how even ground observations of clouds can help give us site-specific information that we can validate the models against. But can you maybe give an example of how that might happen with respect to something that could be measured for the carbon cycle?
Oh,
And then the second question is whether or not the models that you referenced on your last slide, if they interact and how they might interact with one another.
Okay. Oh, I'll go with the first one. So, yes, we're continually like evaluating and challenging the model with observations. And so we have built a large observational database, which goes through a series of diagnostic evaluations whenever we're running or developing the model. And to compare it, so we need to have that as a basis to understand biases in the model, how well we actually pick up processes in the model, and to understand internal variability versus the forced response of the model. One classic example is we've partnered very closely with NEOM, which is the National Ecological Observation Network here in the US. And it's a series of around about 50 or so sites where the National Science Foundation put in monitoring of these different ecosystems across the US. And so they're looking at soil carbon, vegetation. They have detailed flux measurements. They fly planes over the top to do profiling. And so that information is going into the development of the land model and being used to challenge the land model. A lot of satellite products are used for trying to work out energy imbalance at the top of the atmosphere, trying to understand cloud physics. And I think Monica mentioned that. I'm going to go to the second part of that. So yes, we're continually processing and taking on observational data. We also use a lot of observational data to put in the surface data sets. So how do we describe vegetation distributions and both historically and projected based on satellite observations, country level, and maybe even down to county level inventory databases. Things such as river networks have to be taken from existing streamflow networks. And so they have connectivity and understanding of flow rates, those sorts of things. So we're continually putting observational data into this model to try and make it better represent the world, and then to also then use that observational data to say, well, how well does the model work? The second component, which I'm going to get to, is how is it connected to between each of these modeling groups? And they're not actually typically physically connected, such that but they can do intercomparison projects. So the South American Affinity Group did 2 high-resolution simulations of the whole of South America. One with the Weather Research and Forecast Model, WRF, the other one with a variable resolution CSM. And they were both done around about, well, 3.5 versus 5 kilometer resolution. And then they could look at how the 2 models worked, and then they would compare different emergent properties such as rainfall patterns, or like how different convective systems worked, how gravity waves work. And so while they might not be necessarily connected in that sense, they can be compared and they can be used to inform each other. Okay. So
That's great. Thanks, Pete.
all right, with that, I might move on to the next part of the talk, which, and I see it's 9:40 right now, so I'm going to be pretty quick on the second part of the talk. This is a National Science Foundation grant that Monica and I both got last year, and it's looking at climate interventions with CSM. And I'm just going to share my screen. Go. Okay. So this is a what's called a Growing Convergence Research Grant. So it varies slightly in terms of typically National Science Foundation gives you money to go and do research. In a Growing Convergence Research grant, what they're trying to do is say, well, it's great that you can do great research, but to make it applicable and useful for society, you need to integrate a lot more people than just those researchers. And so what we're doing is we're calling convergence research. So what we're doing is we're trying to bring communities in from different places with different skills and perspectives, and help them help us all work together. And this is like something we've got with Arizona State University, Duke University, and Louisiana State University. And we're trying to bring all these different components together. And what we're trying to do is build this Earth system framework that can allow us to investigate climate interventions, and to do it in such a way that we can take that information and make it useful for stakeholders as they're sort of exploring and being challenged by the idea of climate interventions as they're being put through policy and sort of public forums. So these are the principal investigators on the project. So you can see myself and Dave Lawrence, Simone Tilms, who's at atmospheric chemistry laboratory. So she does a lot of work with stratospheric chemistry. Andrea Smith, who's with the COMET program, who's part of UCP. Monica, who's obviously here with me from the Climate Global Dynamics Laboratory. Michael, who's from Arizona State. Cheryl Harrison, Michael is a anthropologist and archaeologist. So he's understanding the human dimension to what's going on, both historically and as we go forward. Cheryl Harrison, who's an ocean biogeochemist and looks at ocean impacts. And Tyler Felgenhauer, who's at Duke, who looks at how do policy and scenarios get built in, how do decision-making processes work. So we're all working together on this project to try and understand how do we start investigating climate interventions. So I'm just going to give a little bit of a background into what I mean by climate interventions. And I don't have to tell very many people, but we're witnessing like increased severity of these major weather events associated with climate change. And we can see down here on the bottom right, we've gone from this much cooler period at the end of the 19th century, sort of through the 20th century. Now we're in the 21st century. We're really seeing strong warming kicking in. And if you go and you look at Paris, the Paris Agreement, and this is the IPC Assessment Report 6, what we can see is that if you look at where we're currently on, and that's if we were to implement like all of the nationally declared contributions and commitments, we're still looking at 2.8 to 3 degrees of warming, somewhere in that line. So what we really need to do if we want to look at hitting those Paris agreements is we're going to have to both mitigate strongly, but also look at other things that will help us limit warming. And even at 1.5 degrees to 2 degrees warming, there's still going to be strong climate impacts that are going to be experienced, but they'll be much less severe than those that would happen on on these emission mitigation pathways as we currently have them agreed to through international agreements. So the question is, well, how do you go about getting to one of these lower warming pathways? And the reality is that, like, when we look at the carbon cycle and what's involved in the carbon cycle, is even if you mitigate out like as much as you can, there's still going to be a lot of non-CO2 greenhouse gases that we'll need to deal with. And there'll be CO2 and other greenhouse gases coming from land management. Even if we were to cut fossil fuel CO2 to zero, we'd still have some element of greenhouse gases that we'd have to deal with. So it looks like negative emissions or some form of beyond mitigation requirements are there. If we look down here in the bottom, we see 4 different scenarios that they have with different mitigation pathways and different amounts of reforestation, afforestation, and bioenergy and carbon capture and storage that came out of the IPCC's special report on 1.5 degrees. But basically it says the more you delay mitigating, the more you have to find some form of negative emissions to offset those fossil fuel emissions that you have allowed to happen. And so what do we also know from the IPCC? Well, we know that like basically there is this what's called transient climate response to emissions. So regardless of which pathway you're on, the total amount of carbon that you emit will respond and tell you how much warming you get in the system. So these are the 5 different scenarios from CMIP 6. And what you can see is that like regardless of how much carbon is emitted in each of those scenarios, the climate response is almost linear. And that's true over the historical period as well. So just looking at, just basically saying, gigatons of carbon, gigatons of CO2 versus petagrams of carbon. It's basically just atomic weights of a CO2 molecule versus a carbon atom. And what a petagram is like, it's this one with 15 zeros behind it in terms of grams of carbon. So this is the numbers that always get put around in these reports, and they're sort of like these magical numbers, but they really are just background chemistry, background molecular mass. So what are we talking about in terms of climate intervention? So the National Academy of the United States National Academy have released a number of reports on this. And so they basically, the first one is looking at mitigation with carbon dioxide removal. So what we can see here in this is you can do reforestation, afforestation. You can look at things such as biochar. You can look at things in the oceans, such as drawing down carbon through increased nutrients, such as iron or other fertilizers. Alkalinity, changing the pH of the ocean affects how much carbon can be brought in. You can also do artificial upwelling, so you change the circulation. And the other side is you can do direct air capture, so you can try and take carbon out of the atmosphere. They all have very big technological challenges, except for afforestation, reforestation, obviously. And they have unintended consequences. We can also look at reducing warming through artificially changing the selectivity of the planet. So this is where we're talking about putting the stratospheric aerosols, such as sulfates, in the stratosphere, or seeding clouds there. As you can see here with this depiction of a boat with putting salt particles into the stratocumulus decks over the low ocean clouds. And then we're also looking at reduction of impacts. So does this really help with adaptation? Does it help with the ability to address the impacts of climate change? So this is what we're really, the fundamental thing we need to know about these modeling is it a better world with climate intervention, or is it a worse world? And being able to do that level of impact analysis and assessment. Okay, I see we're coming up pretty close to the hour. I'm going to leave some time for questions and discussion. This is just the Community Climate Intervention Strategies program that we've been running here at NCAR for like the last 3 years. This is an open community, just like the community Earth system model. We really excited. We'd like to have people join us. I'm not going to go through the rest of my slides because, well, you know, I can go through and just explain what we're doing, but I think a discussion would be better at this point in time. So I'm just going to end here and open up for discussion. I probably could have left it on the last slide, but this is the project we're running right now. And Monica, you know, if you have some things you'd like to add to about climate justice and other efforts you have, this would probably be a really good time for you to do that too. So I'll be quiet now.
Thanks, Peter. Yeah, I mean, I would say that the only thing that we're also trying to do is within a lot of this research, make sure that the questions that we're asking are questions that like various people care about. Because right now we find ourselves in a situation where we need to know whether we're talking about climate change itself, whether we're talking about various mitigation pathways, whether we're talking about carbon dioxide removal, reforestation, afforestation, BECCS, these sorts of things, that the impacts that we're looking at are impacts that people care about. Because we need to know kind of what's going to happen in the future, what possible futures might exist, and be able to choose between them in an informed way. So that's kind of how we're trying to reorient some of the science that we're doing towards justice concerns, is making sure that rather than making assumptions about, excuse me, the information that people want, that we're actually being responsive to their concerns, and talking with them about, well, what sorts of impacts do you care about? Yeah, so I'll just leave it at that because I think we only have a couple more minutes. But I did put in the chat, a couple chat boxes up, the link to that program that Peter was referencing, which is the Community Climate Intervention Strategies program. And I also put in there some information early on about some of the simulations that Peter referenced, which are the SMILE simulations, which are those what we call large ensembles, which just means that we do a lot of individual runs and then average across them, but put in information about those runs. And I think I might have also put in information or an example of a high. No, you know what, I'll put it in now, but if anybody's interested in kind of what some of the high resolution simulations look like out of CESM, the Community Earth System model, which are really cool to look at because you can get things like you can resolve eddies in the ocean, like around the coastlines and stuff. I'll put in a video of CESM and a high resolution simulation too, in case anybody wants to look at that. Yeah, but I guess we'll just take any questions that you might have.
Thanks so much, Monica and Peter. This was such an amazing presentation. So many people have been enjoying it and asking great questions in the chat. And I would really encourage, if anyone has any other questions, to put them in the chat. I did have a quick question for, I think, you, Monica, and maybe this is what you had mentioned just now, is putting in the CESM links allows people to actually go in and kind of play around with the model. Is that correct? Or like you see how the model's kind of working?
So some of the links that we'll put in are videos that people have made to visualize simulations that have been run. So there you can go in and you can kind of see like how the model treats various things. And what I was trying to find was actually there's a video of CESM and others where you can actually see like various tropical cyclones forming in the tropics. But unfortunately, I'm not able to find that video. I might have to send it to you and then you can distribute it to the community. But these are just visualizations to be able to see what the model can simulate. And if you are interested in being able to learn how to use a model like the Community Earth System model, Peter actually just put in there the link to the tutorials, which are a way that you can get acquainted with how to use the model, and then therefore go around and be able to play with the model. Sorry.
You're great. No, that's wonderful. That's super cool. I think we would definitely have some people that would be interested in those tutorial applications. And definitely seeing how it relates to Globe. That was what was really exciting, is mentioning the importance of ground measurements. And you mentioned a bit about clouds and a little bit about the carbon cycle. And I think some folks were, even around the recent volcanic eruptions in Iceland, aerosol measurements are really important during this time to really help understand and validate that model, and get more information around that. So just wanted to, really relate how cool that is, that, the measurements that we are taking with Globe, even if they seem small, they really do add a lot to these larger models.
Yeah, and I'll point out that one of the really important things is having observations from across the globe, right? Because historically, a lot of observations that we have are found in little pockets, which is good because we can, validate the model according to those observations. But we need to know with a global model if it's doing well in all different sorts of places. So having an expanse, right, a broad array of observations from a lot of different locations, regardless of what types of observations those might be, can really help us to determine whether a model does a good job, not just of simulating like one region over here and another region over here, but of doing all the regions, which then add up, right, to kind of the global phenomena that we care about. So yeah, it's really important in all sorts of observations. Some of them we have to interpret in order to make them usable to validate the model. But that's something that we do. So all sorts of observations of the Earth system, which is the model is simulating, are really important for us to have, because they basically tell us whether or not our model is doing something that is close to the truth.
Awesome. Thank you, Monica. And thank you again, Peter. Yeah, I like how you also, Monica's work's observations tell us that we can't trust the model all the time. And then there's some things that, and that's the importance of models, is that they are, prediction simulations, but not necessarily the truth all at once. But they really help us understand what potentially could be happening and what's been happening historically. And all of this data together really helps us get even a clearer picture as we're moving forward. I did want to go back. I was going to say, I think there was one question. I know we have really 3 minutes left. And it was just about which model is used to understand climate. And what I think is beautiful is that all these models are used to understand our climate at local and global systems.
Yeah, so one of the things to keep in mind is that models, even the community Earth system model, which is meant to represent all these different features of the system, the land, the ocean, the atmosphere, they're good for answering certain sorts of questions, but they might not be suitable for answering others. So when it comes to the climate, which is super complex and has all these working parts, we need a variety of different models to be able to answer all the questions that we might have. So the community Earth system model, which is the one that Peter was talking about, is the model that we use to kind of understand, well, what's going on globally, right, with our system, whether we want to understand kind of how heat is impacting various dynamics in different regions, whether we want to know about the exchanges between the ocean and the atmosphere, the land and the atmosphere, so that we can get an account of the carbon cycle. So for those types of questions about climate and what impacts of those different exchanges might be on a larger scale, we have a tendency to use the community Earth system model. But then some of the other models that Peter referenced in his talk, like FATES, that's a model that we use to understand specifically ecological impacts, or the interactions between ecological systems and the climate. And so we still ask climate related questions of FATES, that model, but they're just slightly different sorts of climate questions. And then WRF is the weather model that we have out of NCAR, but it's a model that we can actually run on longer time scales, but at high resolution. So we can get information about local climates or regional climates and how they might be impacted by different warming scenarios like the ones that Peter referenced, which are known as the SSPs. So all of these models to some extent serve some sort of climate purposes, if you will, in that we're asking climate related questions of them. It's just different sets of questions on different sorts of climate topics, if that makes sense.
Amazing. Thank you so much, Monica and Peter. We are at time. So I just want to thank you both again. Also being here while you are both not under the weather. Just really really appreciate your time and sharing all this amazing knowledge with us about these models and how it relates to GLOBE. Thank you all for joining us. We had over almost 300 people register for this, so I know there's going to be a lot of folks watching this afterwards, which is really exciting. So just to let everyone know, this will go up on our YouTube channel. And so if you do have questions, feel free to reach out to our Globe Campaigns email, and we will get those questions off to Peter and Monica. But thank you all and have a wonderful, wonderful day. I'm going to go ahead and end the recording.
Thank you.
Here. Thank you so much.